So we are going to solve a problem. As I promised, I am going to show a problem where the solution involves the analysis of forces, particularly your friction force. Now, in this problem, you are given this. Consider a system as shown in the figure, and block A weighs 45 newtons. So this is the weight of your block A, and block B weighs 25 newtons, respectively. So as you can see in the figure. Now, once block B is set into motion downward, it descends at a constant speed. So that is one of the things that we need to note in the problem. So basically, if it descends at a constant speed, the velocity or the speed in that case is of course constant. So it's not changing, and that means that the acceleration on your system is equal to zero. So this will make all of our calculation um, easier because the acceleration is zero. So for the first question, you need to calculate the coefficient of kinetic friction. Now, if you notice what is being asked in a problem is kinetic friction, it is because of the fact that your surface A actually has a contact with your table here, or the platform on the table there. So there must exist a friction. But since the object A slides over or moves towards the right at a constant velocity, it is rightfully that, or it is appropriate to understand and to know dapat na the friction existing is kinetic rather than static friction. That's why you are asked about the kinetic friction in that case. Now, the whole point of this video is just to show you no on-site changes whenever we try to solve problems where there is already friction. So I would just tell you ahead that there's nothing really strange in how we do it. So we first start still with a free body diagram on body A. Now on the free body diagram on body A, as I am doing here, I have first to draw my axis. So this is basically the same with what we are doing previously, or what we have been doing. Now let's plot the forces. So of course the body A has a contact or support over the top of the table. So a force must exist upward perpendicular to that, and we know that for sure to be the normal force. And also, the force opposite sa imong normal force in this case is the weight of the object A. So I will denote that at W sub A. By the way, I should have denoted this also as N sub A, just to specify that that is the normal force for the body A. Now, secondly, we have tension. So you have a string here, and tension will try to pull with respect to this body A. The string is actually trying to pull that towards this direction. So hence, the direction of my tension should be just there. Now, another the analysis upon of on the tension force is present here. If you try to look at this one, these are just two continuous strings, wala na putol. So they are, I'm hoping you understand it now or recall it now, that the tension on that string should be just the same. So if you don't understand why the tensions are the same in this case, let's say if I call this my T1 and T2, they are just the same. So T1 is just equal to T2. Then check out the previous video on the analysis of tension forces. I will just call them T for brevity. Now I have T over there, and you have to note that the direction of motion is actually going towards this direction. So this is the direction of motion, so D of M. Therefore, we have discussed this one that the friction force will always be opposite to that. So in this direction should be my F sub K, meaning my kinetic friction. So that's my free body diagram for body A. So basically, there's nothing really new about this one because this is what we have been doing previously. It's just that in this case, we now have a new force that we took into account in our free body diagram. So let's proceed with the summation of forces. The same rig hapon yun from what we have been doing. So the summation of forces along x will be given by f of x is equal to ma sub x. Now, since there is no acceleration along x, since it is moving at a constant velocity, a will be 0. So what are then the forces on x? So clearly, we have tension situated to the right, so we have positive T. And then minus F sub k, we have kinetic friction situated on the left side, so that is why you have negative, is equal to 0. So basically, as you can see here, this is your first equation of this problem. So we label that one as our equation 1. Now let's proceed to the summation of forces along y. So this is basically the same, as you can notice from what we have been doing. Now the m a sub y, still the acceleration along y is 0 since it's moving at a constant velocity. And what are the forces present on y? So clearly we have on the upper portion of our along our y-axis, we have n sub a, normal force a, and then minus the weight sub a, because the weight is situated on the quadrant going down. So that is just equal to 0. So in this case, we already have, by the way, let's resize this one. We already have two equations. So I will call this one as my equation 2. So as you can notice, class, there's not really change in terms of how we do things. Maura gyud gihapon siya. It's still the same. It's just that we took into account a new force. In this case, the friction force. Now let's deal with the free body diagram number 2. And this free body diagram is for this body over here. Kining imo ang this body B. So clearly, that's the free body diagram for that is very easy. So firstly, you have the tension T that is trying to pull the string upward. So the direction of your tension force in this case should be upward. So that will just be the direction of the T. And of course, in that hanging case, you notice that body B is actually hanging. So naatay, we have your weight is going down. So that is your weight sub B. So basically, that's the free body diagram for the forces present on B. So let me just put notation here, or denote the notion that this is FBD for, is it B or A? For B, yeah, for B. Now, the same with what we have been doing previously. Let's proceed with the summation of forces along X. So from our free body diagram, you don't have any force along X there, so it will just be set to 0. So this is your, let's say, your useless equation number 3. Now, for the summation of forces along Y, in this case, is equal to ma sub y. Now, there is no acceleration again along Y, since it's moving at a constant velocity. Then the forces along X, let's start from the positive y-axis. We have the positive tension minus the weight along B, that is just equal to 0. So this is then our fourth equation. So fourth equation, equation 4. Okay, equation 4. Now, as you can see there, in terms of the process, class, we don't have any change at all. It's just that in how we wrote the summation of forces, we added this highlighted term, Fk, kinetic friction, which is always opposing or opposite to the direction of motion. Since the direction is motion is towards the right, then the kinetic friction will be written in your FBD towards the left. And in terms of how you write the summation of forces, there's nothing really changing at all. It's just that you incorporate this new force. So maura gyud na siya, wala gyud pagbago. So whenever manggaling, if ever mag-change akong mind to give a problem with friction, basically the same process na imong buhaton. Okay? Now, this time around, let's go back to the problem. I think we have to solve A muna. So you need to calculate the coefficient of kinetic friction. So find the coefficient of kinetic friction, that is just mu sub k. Now, of course, let's try to look into our equations. Now, from equation 1, you should realize then, if you remember, that I will put here, sorry, recall that your kinetic force is just equal to your coefficient of kinetic friction multiplied by the normal force A. So this is telling you that from equation 1, if you try to look at your equation 1, right over there, T minus Fk is equal to 0. So T minus kinetic friction is equal to 0. So as I've written in the recall part, I will try to express Fk is into mu sub k n is equal to 0 because of the fact that we are actually looking for mu sub k. So therefore, I am having t. If I'm going to transpose this to the other side, I have mu k n, but I have to specify that this normal force is on body A, so n sub a. So further simplification, since I'm just looking for mu k, I'm going to divide both sides by n sub a. This one also by n sub a. So what is left in my expression would be mu k. Mu k is equal to t all over n sub a. Now, if I try to look into this one, I will call this my fifth equation, equation 5. And look at t. I don't know t, so I have to find an expression for t or solve for t first. And I don't know directly what is n sub a. So, unknown gihapon na siya class. So, let's go back to your equations. So, from equation 2, I'm hoping you are seeing here equation 2 that you can actually use equation 2 to find kinsaman, to find NA, this term here. Makuha ni mo na from equation 2. So I'm going to write here this one. From equation 2, I have this expression. NA minus WA, NA minus weight sub A is equal to 0. So this tells me that NA is just equal to weight sub A. And take note that weight sub A is actually given in the problem. And that is equal to this value over here, 45 newtons. So this is telling me that NA is equal to 45 newtons. So I'm just going to highlight this because we are going to need that value later. So this is telling you then that si NA ni mo diri solved na, kabalo na kaana. So no problem with NA now. However, you still don't know T. So let's go back to our equation where we can scout a value for T. Okay, so I'm hoping you are eyeing what? Equation 4, right? Because you have T and some value over there. So equation 4, let's deal with equation 4. Okay, wrong color. So from equation 4, you have this expression. T minus WB is equal to 0. So T minus weight sub B is equal to 0. It tells us that T is equal to W sub B. And what is W sub B? That is also given in the problem. So the weight of B is actually 25 newtons. So the tension then will just be W sub B or 25 newtons. I'm going to highlight this again. And this tells me then that this T that I'm seeing over here is something I have already solved the value for, right? So that means to say I am now ready to solve this equation. So mu sub k, which is the coefficient of kinetic friction, is just equal to the tension divided by the normal force A. Now the tension, as I was able to solve here, is 25 newtons divided by the normal force A. I have also solved that earlier here, 45 newtons. Now this is a good sign because as you can see, the newtons will cancel out. Since this is just a coefficient, it must have no value. No unit. So when you do your calculation, that will give you that your mu sub k is approximately equal to 0.56. Yeah, that's 0.56. So this is now your coefficient of kinetic friction. Okay, so I'm going to summarize what is happening here. Basically, walay nagbago, nothing changes with how we do our previous calculation. It's just that we now try to incorporate the correct direction of your friction, in this case kinetic friction, since it's moving. And then you just have to incorporate also the friction in your summation of forces. Then you just proceed as usual in how you solve your problems, as you've learned previously. Okay, so I'm hoping this is somehow enlightening in terms of how we solve this problem, or how we solve problems involving friction. Okay, so that's it for your online class today. And I will be posting a conceptual test. So be honest in answering the conceptual test on Newton's law, so that I will be able to gauge whether you have understood fully the topic, so that I can review if ever there are areas na wala kang nasabtan. Okay, so see you on the next face-to-face session.